This video is on AP Physics C 2024 solutions set to question number 1, the actual exam. So let's read this one out. Blocks A and B, so A and B, of masses m and 2m and m respectively are arranged in a setup consisting of a ramp that makes an angle of theta with the smooth horizontal table and an ideal spring constant K fixed to the wall. Block A is held at rest at a distance of d up the ramp, so the slant distance is d capital D, and B is at rest on the horizontal table. The coefficient of kinetic friction between A and the rough ramp, okay, so this ramp is rough. Coefficient of friction is mu in the region of length d, and there is negligible friction between the blocks and the smooth table. Okay, so there is no friction over here. At t equal to 0, block A is located at horizontal position x equal to 0. So this is t equal to 0. This is the starting time. T1 is when block A has traveled a distance d down the ramp and has transitioned to the table and moving with speed v at x equal to x1. So over here, the block 2m is moving with a speed of v. I'm sorry, just v. And T2, block A is at x2, and when it collides and sticks to block B. So this is where the collision happens and it sticks to it, 2m. Okay. At T3, the combined blocks A and B are at x3. So this is where the combined blocks are. So this will be the big box. And if it's combined, then 2m and m will become 3m. When they collide with and stick to the spring in its equilibrium position, and at T4, the combined blocks A and B are instantaneously at rest when the spring is compressed a distance of xc from the equilibrium. So this is where the blocks ultimately come, and they come instantaneously at rest while the spring has been compressed with xc. Okay, this is the scenario. The question asks about derive an expression for the speed v of the block A at T1, and the answer should be in terms of these variables. So at T1, what is T1 by the way? T1 is at x1, so this is T1. So I think we can just conserve the energy, but please be advised that the mechanical energy is not conserved, but the total energy is conserved because there is a friction here, so that is supposed to be taken into account. So we are going to say that work done by the energy at, let's mark this as position number A and let's mark this as position number B. So we are going to say that work done by the friction plus the mechanical energy at A is going to be equal to the mechanical energy at B. Okay. There's no spring involved here because between A and B, the spring is obviously at equilibrium. At what is work done by the friction? In fact, work done by any force is F dot T. So friction force dot the distance traveled. Mechanical energy at A, I believe, is only potential energy because mgh. So mgh. Now the question is, what is h? So we have to be careful here because h is the vertical height, which as of now we do not know. So we need to use a little bit of SOHCAHTOA, but yeah, we'll do that in the next step. Any other energy? No spring, no kinetic because it's released. So that's it. At B, the mechanical energy will just be the kinetic because again, there's no spring. There's no potential because it comes at, at the ground level. So this will just be a kinetic energy, which is half m is 2m, and v square. And we need to find the speed in terms of the other things. Okay. Now, what is friction? So for friction is obviously mu times normal reaction. First of all, let's deal with the dot product as D. And I know that the dot product is going to be come out with a negative sign because the block is moving here and the friction is on the other side. So it's cos 180 and cos 180 is -1. So I'm going to put a minus sign. What is friction? Friction is mu times the normal reaction. And what is D? D is capital D plus 2mg. Now, what is H? For h, we need to do, I think, sine. So because sine of theta is opposite over hypotenuse, so sine of theta is going to be h over capital D. This is what is going to happen, right? Capital D goes over on the other side. So h becomes d sine theta. So that's what I'm going to replace here. d sine theta. Okay, half of 2m will become just m, so mv square. Okay. Now the question is, what is normal reaction? So for that I need to make an FBD. This is the normal reaction here. This force is going to be a component which is 2mg sine theta, and this is going to be 2mg cos theta, and this is going to be the friction force. So the normal reaction is obviously equal to 2mg cosine of theta. So I'm going to replace that with 2mg cos of theta, capital D, plus 2mg capital D sine of theta is equal to mv square. I think the m is cancelled from both the sides the way I see it, because if we divide both sides with m, the m is gone. And finally, I can just isolate v from here. I'm just going to need some more space. Let me copy this and paste it over here. So from here, if I rewrite the left side, that's going to look like 2gd sine theta, just writing this first, minus 2 mu g mu g d rather cos theta is equal to v square. So the value of v comes out as square root of, and I think I can safely take 2g and d as a common factor. So I'm left with sine theta minus mu cos theta. Yes, these were all the variables for which we were supposed to use. So I think that will work, right? That should be our final answer. So yeah, this is what we have here. Let's talk about the next question. We have an expression for the spring constant K. Okay, so spring constant K of the spring. So I think for a spring constant, once again, we can conserve the energy. But before conserving the energy, we definitely need to find, we need to take this perfectly inelastic system or collision into account. So let me just take this entire thing so that I don't have to go back and forth. Here, first I'm talking about, let's take this as now the, uh, uh, sorry, at this point, 2m is going with v. Obviously, we know what v is now. We are going to sub that in later. But we are going to do the perfectly in elastic collision. So you're going to say that initial momentum, which is 2m times v, is equal to the final momentum. Final momentum is 3m, guys. Why 3m? Because they stick to each other, and let's say v2 is the new velocity after they stick together. So m and m is gone, so I'm left with 2/3 of v is v2, or v2 is 2/3 of v. How's that going to help us? Because now I'm going to conserve the energy. The energy at this point, by the way, guys, if you're thinking that you can conserve energy at this point with the spring energy, that's going to be incorrect, because during perfectly inelastic collision, some energy is lost. So you have to take the energy after the collision. I hope that makes sense. So initial energy is going to be only kinetic, which is half m v square, right? And the final energy is going to be k over 2 x c square. 2 and 2 is gone. Okay, so I think I'm going to rewrite this here. K x sub c square is equal to 3mv2 square. What do we have to find? We have to find spring constant K. So K is 3m over xc square times v2 square. Now what is v2 square? v2 square will be obviously be the square of this one. So what is the square of 2 over 3v? That's going to be 4 over 9. 4 over 9 times v square, right? V square. Okay, 3 times 3 is 9. So we have, this is cancelled. So K is 4m over 3x sub c square times v square. And what is v? V is this entire thing, and it should be squared. So we'll do away with the radical. So we are just left with 2gd multiplied with sine theta minus mu cos theta. And finally, 4 times 2 is 8. So the final answer will be 8 mgd divided by 3x sub c square. and the rest of the thing is just sine theta minus mu cos theta. So that's going to be the answer for the spring constant. Obviously, that's not an expression which you like, but yeah, this is the answer, whether we like it or not. Okay, all right, excellent. Let's move ahead to the next question. Now, they're asking that on the following axis, sketch a graph of the magnitude of the momentum of block A as a function of time from 0 to 4. Interesting. So, if we talk about momentum, what is momentum, guys? Momentum is mass times velocity after all. So, mass times velocity of A. Now, the velocity of A, we're talking about A, okay. From, okay, till T1, okay, all right, interesting. After this, after reaching at this point, I don't think the momentum is going to stay same till x3, in fact, till, sorry, till this point, till x2, because at x2 it collides obviously. So if x2, if it collides at x2, then obviously the momentum changes. So I know that the momentum is going to be, and T1 is, I think, x1, right? Let me go back and verify. I think T1 is the block has traveled distance t down and transition to the lamp is moving at t equal to t1, the block has traveled a distance d down the ramp and has transitioned to the table and is moving with a speed of v at x equal to x1. That's a little confusing. At t equal to t1, block A has traveled a distance d down the ramp, has transitioned to the table, and is moving. I think this is t1, the way I understand it. It should be t1 because at t1 it is at x1. Yeah, I'll take that as t1. Yeah, okay. So yes, t1 is this point. So I know that somewhere in between, because obviously before t1 it just becomes constant, right? And till t2, this is the point t2. So before t1, from here the speed is going to remain constant, so the momentum, so is the momentum, so it will become a straight line. It's not going to change till t2. After T2, it's going to collide and the momentum suddenly drops, right? Suddenly drops because obviously the speed is going to change because that's a bigger mass right now. In fact, if we already did that, right? The new speed is only 2/3. So the momentum has decreased. So it will come over here, a sudden drop. Then it will go likewise at till T3. And then some interesting thing is going to happen at the spring. We are going to talk about that in a minute. But what happened over here? I think over here there was a continuous, there was a constant. Um, well, obviously it increased. So initially it was 0. Now the question is whether it increased in a linear fashion or not. So velocity is and the way I see it, we can use equation of motion here. So the velocity v is equal to v naught plus at, right? V naught is anyway 0, so it's at. There is an acceleration, whatever it is, it's a constant. So it's linearly dependent on time. You know, v is equal to at is like y is equal to mx. So it's gonna increase in a straight line fashion in this way, right? Okay, now the question is how will the spring velocity change over here? So I think over here we can use the formula for the velocity of the simple harmonic motion. I know that here x is going to be equal to x naught or whatever a cos sine omega t. Why am I using sine omega t? Because the SHM kind of starts at the equilibrium position. So at t equal to 0, x is 0, and yes, this is what it starts from. It is at equilibrium position. So what will be the velocity? The velocity is obviously going to be a omega cos omega t because I just found the derivative of this. And I am interested in momentum. So obviously momentum has velocity. So the curve of momentum is definitely going to be same as the curve of the cosine. So this is what we have. Initially the velocity was maximum and then the velocity is zero, and it's going to follow a cosine curve. So that's going to look like this, you know, because the cosine curve obviously is, like this, if you agree with me. So we are only interested in this portion. So this is how it's going to be. It's going to be at the maximum, but using the cosine or following the cosine curve, it's going to decrease and eventually come to zero. So this is an interesting question, and this is how we do it. So linear increase till some point where it comes at the bottom of the ramp. So this is the time when it comes to the bottom of the ramp. Then it travels till t1 at the same velocity till collision, decreased, and then cosine. Right, I hope this makes sense. Let's move on to the next question. Use principle of forces to justify the graph you drew in part P1 for the time interval T3 and 4. T3 and 4 is the cosine one. Explicitly reference the features of the shape of the graph you drew over here. Okay, so if we were to use the concepts of the force here to describe it, so let's look at the attribute of the curve. Obviously, it's concave down, and I know that momentum just be replaced with, can be realized as a velocity as well because the mass is anyway constant. So this is in a way the situation of the velocity, and the rate of the change of velocity is decreasing here because this is a concave down function. It's getting more and more, steeper. So how we can how can we justify this? We are going to say that initially at the time of collision, there was no force, right? Because the spring was at its natural length. So the velocity was maximum and the F of spring, F of SP, F of spring was zero. But as the block started compressing, as block uh, started to compress the spring, the force of spring increases, obviously towards the left side. And where was the velocity? Velocity was to the right side. So F spring increases on the left side. Velocity is towards right side. Velocity is towards right side. This means that there is a deceleration. If there is a deceleration, this would imply that the object is slowing down. So this justifies the shape that why it is coming down, why it's not going up. So that's why it is coming down, because of the continuous force acting in the opposite direction. So it is slowing down. So that defines so that's why the graph is decreasing in nature. That's why the graph is decreasing in nature. So this is the first aspect of it. Now the second aspect is, why is that concave down? Why not concave? Why not concave up? Because it could have been concave up and decreasing as well. That's because the slope here, if you look at the slope is continuously getting more and more steeper, more and more steeper. Why is this happening? Because as the block started to compress, the F spring is increasing. Just from this statement, I'm just going to copy and paste again. So as the block started to compress, F spring increases towards the left side, which means that the acceleration also increases towards the left side. And acceleration increases, this means that the block becomes, the curve becomes more and more steeper, right? More steeper, and hence the curve is concave down. So this is how we can justify why the function is decreasing. That's one. And second is why the function is eventually concave down. I hope this makes sense. I think this was the last question. Oh, no, there's another question. For times t greater than t4, what is t4? Oh, t4 is where, okay, all right. The two block system oscillates with time period t naught, and the procedure is then repeated using a new ramp where there is a negligible friction between A and the ramp. Indicate how the new period of oscillation in the procedure that uses the new ramp compares with the period of oscillation T naught from the original procedure. So what they said is the procedure is then repeated using a new ramp where there's negligible friction between the block A and the ramp. So eventually the energy is entirely conserved, right? If energy is conserved and there is no friction, obviously there is going to be more speed, right? As there's going to be more speed, this will be more, this will be more, everything is going to be more. First off, what is the equation of the time period? The time period is given by 2 pi square root m over k. But do you think that this is going to in fact change? Obviously m is like, I'm not saying m is m, m is the total mass. So what will change over here now? Nothing, because the total mass is still whatever it is. It is 3m, right? Whatever it is, it's 3m over k. K is not changing, m is not changing. So why will the time period change? Whether you make the initial block even frictionless, the velocity will change, but the velocity is not going to impact the time period. So the time period is going to remain the same, and this is our justification because these two things are constant. But I hope this question makes sense. Any questions, please post it on the comment section. I'll see you in the next video.